One of the things that I've been trying to do since I took on the program hat is listen to what people say during our, gathering time before the meetings start, and also talking to people as I pass through the gallery or, work on some kind of project with members. And so the seed for tonight's meeting came from one of those kinds of conversations. Um, there's always questions about what temperature do you fire at? Is my kiln firing properly? What's happening with my cones? Is this all working the way it should be? I'm not getting the results that I want. How can I better monitor all of this? And so I took that as an opportunity to make contact with the Orton Ceramic Foundation and came up to meeting Tom McEnerny, who is an engineering manager there. And he's responsible for pyrometric products. So he is with us tonight. I have forwarded him all of the questions that people sent to me when the call for questions came out. And I will thank him for staying up because it's 10 o'clock in his world to be with us. And I'll turn the program over to him and he can present. And when he's done, we'll open up the conversation for questions and answers. So thank you. And Tom, it's all yours.
Thank you, Barbara. You all hear me fine? Okay, good. I'm going to start sharing my screen so that you can follow along with me. Let's see, I've got a PowerPoint somewhere. There it is. And okay, what I'm going to talk to you today is the evolution of the evolution of how the Ceramic Foundation came into being. And then through that, I'm hopefully going to be able to answer several of your questions that you all had given to me to begin with. So just first, my background, I'm a ceramic engineer. I graduated a long time ago from Ohio State University with a degree in ceramic engineering before they changed the department from a ceramic engineering department to material science. It still offers that as a degree, but is material science, not ceramic engineering. I have a little bias towards that. I think they should go back, but that's okay. So I've been at Orton now. April 1st is actually going to be my 21st year at the Ceramic Foundation. And I was fortunate to take over from the previous ceramic engineer who had been at Orton for 40 years. And he taught me as much as he could of the history and the how to make cones so that they're consistent and reproducible, and the benchmark for measuring heat work in the ceramic industry. All of that was originated from what Edward Orton Jr. had set up in his business. So I'm going to start here with what you see in this first slide is the doorway to the original factory that Edward Orton Jr. had built off-site from the university to produce these pyrometric cones. What's really neat is the reason I say from clay to clay is to what you see right above the door in Latin. You see the words ex argilla ad argillium, and that is the Latin phrase from clay to clay. So I thought that was really neat that Orton had done that, and I love to share that as my introduction here. This is a picture of Edward Orton, probably taken in his 60s, several years before he passed away. But this is a framed picture that we have at the foundation as well as a couple others of him. Um, you see, he was born in 1890 or 63, and he passed away in 1932. A little bit about his background and family. They were born. His family came from the East Coast. He was born in Chester, New York, and he was born to a family. A lot of the Orton family were farmers, but there were several of them that got into academia, and there were a few that got into the ministry or pastors. And so they moved, his father moved the whole family to Ohio when he was the age of 2. The reason being that his father was offered a position to become the first president of a newly formed college in the state of Ohio. And that was to be eventually the Ohio State University. So Edward Orton was exposed to academia from a very young age, and he hung around the Columbus area and Ohio State, and therefore ended up enrolling in school. And you can see on this slide, he graduated from Ohio State in 1884 with a degree as an engineer of mines. From that position, he was able to get work outside for a period of time, which that ended up bringing him back to the university. I'll get into that, what the history of all that was later. But so he is also instrumental in forming the ceramic engineering curriculum, the first college in the university or in the United States to actually offer that degree. And he started that at the university, Ohio State University, in 1894. He was the director of that department through 1916. And during that period, he also served twice as the dean of the College of Engineering at Ohio State. So he really elevated himself to a pretty high prominent level in the university and in the ceramic because of the numbers of engineers that he was graduating. His name was being elevated as he went along. He also decided to organize and become secretary of the American Ceramic Society, and he served there as the secretary, and eventually he was and the honorary president for 1 year. When World War I broke out, he actually, I think it was at the age of 50, re-enlisted, and they made him the rank of colonel, and he served through that. And then at the end of that war, he was involved in drafting the National Defense Act of 1916. This is all history. Just that basically what I'm trying to do is round out that the whole person of who Edward Orton was somebody that got himself involved in a large facet and number of things. He was a forward thinker. He was just always thinking of how can I make myself better and those around me better. Let's see here. Okay, so having graduated from Ohio State with that degree in mines, his first real job was to become a superintendent of a brick plant that had 2 locations, one in Kentucky and one Ohio. And while he was there, I found this quote in some old documents that we had, where he had said, "Trade secrecy, that child of unenlightened selfishness and the foster child of ignorance, has characterized the early history of every art, craft, and industry evolved by mankind. The ceramic industry is no exception to the rule, though the atmosphere of mystery has hung about longer than it did with metallurgy, glassmaking, and other ceramic arts." So what does he mean here by that? He's saying that he's out in the everyday business world. He's trying to solve problems, trying to make product. And those he's working for are telling him, don't share any of what we do with anybody else because what we do is unique. And he really quickly realized this brick plant is not any different from that brick plant. What they're doing, and they think their process is so unique, is no different from the guys in Indiana or down in North Carolina. It was kind of frustrating to him to see that no one wanted to share information. So he also noticed that not only is the information being closely guarded, but they're not really using engineering principles to solve any of these problems. They're using gumptions, common sense, trial and error. They're just fumbling over things all the time instead of using science to find the answers. One of the main areas that he encountered at this brick plant was with the kiln foremans. They were using their instinct as to when did they shut the kiln off? When is the firing done? So he would observe them taking the brick off the one of the spy holes and looking inside at the color of the inside of the kiln to make a judgment. Oh, it's glowing red hot. It's time to turn the kiln off. It was purely subjective, and it was always up to interpretation. Or you could have things like atmospheric conditions affecting the actual result. Is it a cloudy day? Was the sun out that day? Is the wind blowing? Was it raining? There was too many factors that actually caused a lot of scrap basically to be made. And that just frustrated Edward Orton to no degree. That plant that he worked at eventually went out of business. That is what landed him back at the Ohio State University. So prior to 1896, there was no real way of regulating firing processes in the United States, and no method of comparing one factory to the other, or even across industries. So sanitary ware, pottery, artware, all of this was kind of subjectively done. There were some innovations, but nothing really was being widely used. So he is said here is, I entered the manufacture and sale of pyrometric cones with the purpose of performing a definite and needed service to the industry by enabling them to control the firing of the product, which is the weakest part of the process, and facilitate a freer exchange of information regarding the firing process, making it more of a scientific, and you can see here what he said there, which is great. That was the whole impetus of why he ended up making these cones. But where did he ever get the idea is kind of the first question I would come up with when I started there. So I found out that he was in academia, always reading, always looking for things, and he heard about some work in Germany. There was a scientist who had published his work in a journal in the European continent, and his name was Hermann Sager. He had worked at a couple of porcelain tile manufacturing plants, but in those plants, they were using some ceramic bodies that were designed to slump, and use those to judge when a kiln would be fired properly. He then decided that a slumping bar or a body could be improved upon. And so he then created a series of clay bodies, which were more closely associated with glazes than bodies. They formed the glass. And his whole concept was based on the silica to alumina ratio in the bodies that he was working with. And he formulated them by the mole ratio of silica to alumina. So there was a step-by-step progression as you went through these bodies. Orton read this, was fascinated by it. Actually, he first translated it to German, and then or from German to English, and then was able to formulate his own series here in the United States. So the first series started with cone number 1, and I think it ended at cone 36. And through his transposing from German to English, he was able to see where Hermann Sager used the word Kegel to describe his invention. And the German word for Kegel it's a bowling pin, but the closest thing that Orton came to in English was cone. So he's like, okay, he's making cones. And he then decided to use the word pyro, meaning that fire, and a word for measure, metric. So he came up with this pyrometric cone, and that's the whole evolution of how that ever came about. So he founded this company, and he started producing these cones at the Ohio State University in the basement of one of the buildings, but it got too big for that. So he had to actually move it off-site. And he continued to he said he then had, over a period of time, no children from his marriage. So he was thinking, what am I going to do with this company? It's starting to really become something. I don't want it to die out when I die out. So he conceived this idea in the 1920s for how he could create this foundation, basically to convert the company he has created into an entity to further the ceramics industry through the profits that are generated from the sale of these cones. So he's said here to continue the manufacture and sale of the highest grade pyrometric cones used in industry, and use the income and excess business expenses therefrom to advance the ceramic arts and industries in the United States. So here we are at the factory that he actually built off-site, and this building is still in Columbus, not being used today by the foundation, but it has been sold to another organization that is placed this building in the National Historic Archive, so that it won't ever be torn down. It's a historical place considered now, but beautiful building with 3 levels, and they used to bring the materials into the bottom, use an elevator to bring it to the top floor, and then everything would come from the top floor down to the outside. So he really designed and built this building with the purpose of making and efficiently getting those cones out to everyone. So it just was too much after a period of time for even this building, and so they had to start looking for an off-site location, and they found property up in Westerville, where we currently are. And so our home right now is in Westerville. We have a kind of a sprawling 7-acre site with several buildings that are interconnected. And our newest addition being the materials testing laboratory that we added in the year 2012. So back in the 20s, he started to think about this establishment of the foundation, but it didn't happen until his passing away in 1932. And in this will, he established the trust for the Edward Orton Jr. Foundation, and it would be governed by a set of trustees. And he chose these people specifically for carrying on the operations of the foundation. He thought ahead and realized that just making pyrometric cones wasn't the end all, that he should write the wording in this to be such that the board of trustees would have the leeway to decide upon going into other areas of business if they saw the need for it. And so here we had the president of Ohio State was initially started out as a member, the dean of engineering, the head of the materials department, or the ceramic engineering department at that time, the executive director of the American Ceramic Society, a representative from NIST. Now, NIST is the National Institute of Standards of Testing, which is important because we actually sent cones to that organization, and they established them as a standard and published their results, so that now that is why we can say that we are the standard pyrometric cone company. And then we have an at-large representative from the ceramics industry would sit on our board. This initial list of people has been changed over the time because the president of Ohio State University really doesn't have time for sitting on a board of a small company that is making pyrometric cones and thermal analytical instruments. So he has been removed as one of the members, but we still have 5 that sit on our board today. And they have developed a mission statement for us. And it is that we are to provide a stable and sustainable business to support the monitoring, control, characterization of thermal processing of ceramics and related materials, to support their studies through research and overcome technical and manufacturing difficulties. So we're doing that through the dissemination of the information that we get. So this is exactly what our purpose is what I'm doing today, is to talking to you all about what we do and our purpose. We are formed now into 3 distinct business units. We still make the pyrometric cones, but we've also expanded into other devices that measure temperature. We've developed what we call temp checks, temp tabs. PTCR is a product that we resell. That was, and I'll describe what these are later on in the presentation here. The VentMaster is a patented product that we came out with in the late 70s that is designed for venting electric kilns and small studio kilns, not gas-fired kilns, but those that are just mainly fired electric. And we've also broadened. In 1964, we got into making instruments for measuring thermal properties of materials. The first one was a dolotometer. Then we started into custom furnaces, and we got some glass testing instruments. And then in the 1990, we actually brought a testing facility on site, and we do testing on glass, refractories, ceramic materials, and we've even done some work in composite materials now and some metals. So the pyrometric products that we do make, we have the cones, we make those, and I'll show you what the 4 different types are in the next slide. The temp check and the temp tab are products that are sold into mainly the brick industry, the tile industry, and some advanced ceramics industries. They're round discs that we have precisely made with a certain composition that shrinks a great deal when they're fired. And the amount of shrinkage is what we've taken and calibrated that shrinkage so that you can take a micrometer to a fired part, and from that micrometer measurement, you can equate to an equivalent firing temperature. The beauty of these products is they can be placed, like in a brick firing, you can put them in between the brick hack, where there's slots between the brick, and these fit very nicely in there, and they can be retrieved after the fact. Cones can also be used there, but they take up a lot of real estate, and you need multiple cones to be able to do the same thing that one temp check can do. PTCR is like a similar version to the temp check. They're smaller, they're a little more fragile, but they were mainly developed by a company called Philips Electronics, and they were used primarily in the firing of semiconductors and advanced ceramic materials, capacitors, transistors and things like that that are electronic ceramics. They're small, they can fit, they don't take up a lot of space in their firings. So they developed that series of product. They didn't have a distribution channel as well as we did. So they contacted Orton several decades ago and asked if we would be their representative to distribute the products in North America. And we've been doing that for now almost 30 years. So here are the 4 types of parametric cones that we produce today. The large cone, which you're probably mostly familiar with as potters. We sell a lot to the pottery and in industrial industries, where these have to be placed into a plaque to hold them upright. And you put a series of them in either a clay pat or this, what you see here is our preformed plaque that'll hold 4 cones. Next to that is a small cone. They can also be placed into a plaque, but they're only 1 inch tall. They're a little harder to position and a lot more difficult to interpret because they're smaller. But most of the small cones and the ones below that, the bar cones, are used in electric kilns that are equipped with a device called the kiln sitter. And that was something that was developed by a mechanical engineer in California. Kind of a neat story. His name was Dawson, and his in the height of the ceramic hobby industry, when everyone was getting an electric kiln and trying to do hobby ceramics at home, his wife also got a kiln, and he would come home from work and his wife would tell him, dinner's not ready until the kiln shuts off. Would you go in and watch it? And then as soon as it shuts off, you know, cuts the temperature, you watch those cones in there and then shut it off. And he wanted his dinner when he got home, so he got tired of waiting. So he thought, I'm watching these cones bend. Is there any possible way I could develop this a device to shut the kiln off based on these cones? And he was brilliant. He created this thing, and if you might be familiar with it, a kiln sitter, where you take the cone and you place it on 2 metal supports with a rod on top of it. And as the cone bends, it would slump, and that rod would drop down inside the kiln. And on the outside of the kiln, it was holding up a weight held by a claw, that when the claw lift up, it would release the weight and the kiln would then shut off and trip the kill switch to the kiln. So he created this thing, what he called a kiln sitter, like a babysitter. So really neat device. And it's allowed us to sell multiple small cones and bar cones ever since. So thank you to Dawson for creating that. Now, the most current, newest invention in cones is the lowest corner there, the self-supporting cones, developed in the 1970s. So they're the newest of the family, but they are designed to not have to be held in a plaque. They stand on their own, and the angle at which they're held is fixed, so that we can actually predict with a self-supporting cone the temperatures to within 2 degrees C accuracy, which is just phenomenal. You can approach that same accuracy with a large cone, but you've got to be precise and very controlling in the height that you mount the tip of the cone to, and making sure that you've got that 8 degree from vertical just set perfectly, or else you're going to have some issues. Here we have a picture that I've taken of a board that I glued all the cones that we've made to, and I use this as a reference for any new employees that we have to come in, to show them we make, you know, everything from the 022 in the top corner all the way to cone 42, and what different shapes that we actually make that specific composition into. So we can make all these. There's over 80 compositions of cones that we make, and we utilize materials very common to the ceramics industry to make these from, purposely because we didn't want to get unique or hard to find materials that would run out over a period of time. We'd have to find some alternative for it. So we stick with the basics. We use kaolin, like kaolin from Florida. We buy ball clays from Tennessee. We get glass frits made from a glass frit manufacturer in Ohio. We buy the red iron oxide from a company in Cincinnati. The feldspars that we'll use will come from South Dakota. We'll get nepheline syenite from Nefton, Ontario. The silica flours that we'll use, were the flint. We get that from West Virginia, and we're just finding all of our materials local, within the United States if we can. And like in the case of the Nef syenite, we'll go to Canada to get it. But all of these deposits are large deposits that are hundreds of years worth of material. So we also will take those materials that we use as the building block for our products and buy them in truckload quantities. And when we then combine them together in a mix, we know that we're getting a truckload of flint that is going to be stable for a whole year to maybe 2 years worth of products. And then we don't have to worry about shifts in raw material behavior as often as someone going out and buying a 50-pound bag from, say, Laguna Clay, and then coming back a year later and getting another 50-pound bag. Well, it could be from a totally different part of that clay deposit that came from. And there would be drift that you'd have to figure out, is it exactly the same? Well, what we do at Orton is we try to minimize that by buying larger quantities and then characterizing it for the cones that we're putting them into. The building block for everything is silica flour. That is probably, for the vast number of cones that we make, it comprises upwards of 50% in some cases of the formulation. And one, I'm going to give you a complete, you want to make your own cone number 36. I'm not going to lose any business from that, but it's just kaolin, nothing else, just kaolin. And if you want to make cone 42, straight alumina oxide. That's all you need. Some of the machinery that we use to make the cones is in this picture here. The top one is a V blender. So we would then weigh up our materials and we'll add it to this V blender. And as it spins around, it will split and recombine the materials as that is, the V is either pointing up or down. It would actually do the splitting and combining action. We get a very good homogeneous mix by using a mixer like that. The one to the left of that is you can't really determine the scale of that, but that is about a 5-foot diameter and 4 foot tall, and it's a IRIC mixer, and it's a high intensity mixer that is where we're taking and adding our binder, our water. If we're using a clay body that is pretty much white, we would add a food colorant to it to distinguish between the different cone compositions. And then we would add water to this, and it spins at a very high rate of speed and counter current to the mixing action of the blade. So it's almost like you took a washing machine, you tilted it, and as it's spinning around, the blade inside is whipping around in the opposite direction, and it's forming small granules of almost like small snowballs of material. And that's what we're forming in that mixer. That is then passed on to the presses that we use to form the cones. I have a short little video here. If I click it, I hope it'll play, and you'll actually see the hydraulic press forming a couple of strokes of cones. And what you're going to see when this turns on, hopefully, is that the powder is being pushed over top of the cavity, pulled back, and the material gets deposited into the cavity. It moves back. The punches that you'll see, the metal forms come down, squeeze the material to form the cones. Then it moves up out of the way, and then the feed shoe comes forward again, but pops off those cones that were formed and starts the process over again. So I'll just, hopefully this will play here. There you go. So what you saw there is we're making 4 cones at a time, 2 cones per cavity. And the reason for that is the cones, when they're formed as pairs, we can control the density in that cone so that the edges along the die cavity are going to have a lower density than the center cavity of the cone. So when you break those 2 apart and you mount them on your plaque, the side that has the least density will be the bending face of the cone. So we figured out that you can actually control the directional bend of the cone by forming them as pairs where the bending face sets on the die cavity, the wall of the die cavity. Interesting little snippet for you. Okay, so we talked earlier about our dilatometer, and what it does is it is a device that measures the expansion and contraction of a material as it's heated and cooled. This device is really great for anyone who's wanting to develop a glaze or a clay body, and you want them to be able to mesh together and not craze when the glaze is fired or when the body's fired. Or the other opposite end of that is you'll get shivering, where the glaze will just sheet off of your piece and won't adhere to it at all. You can actually measure what we call our coefficient of thermal expansion using a device like this. And it's just a really great tool for being able to quantify how much that material is going to fit when you're forming a glaze and a body. So you want to actually have your measurement of coefficient of thermal expansion of your clay. And then when you formulate a clay or a glaze on it, that glaze wants to be put under compression to the body. You want it to squeeze down, but not too much. So the coefficient of thermal expansion of the glaze has to be that much different from the body to be able to put that under there. This device allows you to get those numbers. All right, there we go. And we have a whole suite of glass testing instruments that if you get into glass weight work and you want to know when the glass begins to soften or elongate, like if you're wanting to pull a fiber, is there any crystals that'll form in this glaze or the glass? These devices are able to do that. We sell a lot of these into industry that is making glass for automotive, or even a lot of your cell phones now have that Gorilla Glass on it. We're selling a lot of these instruments to the companies that are in China, actually formulating these glasses for Apple or Samsung or those kinds of companies. It's nice that we are actually an exporter of our technology to countries like China and outside of the US. whereas most of the time you hear it's the other way. So we do a great deal of export for a small company that is located in Westerville, Ohio. We sell boatloads of cones and instruments to countries in Europe, in Australia, New Zealand, China, the Asian continents. It's just amazing to me that we are able to do that. And in lastly here, you can see this is our materials testing laboratory where we can perform over 70 different ASTM tests on materials to get a thermal behavior, mechanical behavior, physical property. You name it, we could probably do it if there is an ASTM test for it. So what are some other ways that we are supporting the arts industry? We hopefully you've heard of this one. The Orton Cone Box Show is a juried show that is done every other year. They have a competition where you could submit an item that can fit within the confines of an original Orton cone box. And it has to be, most of it, vast majority has to be of a ceramic material, but you can utilize some other things, like some people use metal items to make a point. But here they have actually used, in this picture, pyrometric cones to simulate the nails and a mummy sitting on top of it. Is kind of a cute little thing that somebody did years ago. But if you wanted to look up the Orton Cone Box Show and submit something yourself, you might have a piece of art that you want to have included in this show, you can find that information from the website that I have listed there. Also, we have partnered with the American Ceramic Society just recently for some professional development seminars so that we can teach technicians skills in how to work with ceramic materials. So we have a refractories class that we're teaching and a glass class that we're going to be teaching. So if you have any nephews or nieces or young adults who want to get into the field of ceramics and they don't really want to get a 4-year degree, you can then come to the American Ceramic Society and take some of these online courses, and you can sign up for a certificate in materials and technology. And there are jobs in companies all over the United States where you could land a position and work for them, having some of this background. And on our website, we have, you have to go to the pyrometric or the pyrometric cone section, which is underneath the heading temperature verification products. And inside of that pyrometric cone area, you're going to see a resources tab. If you were to go through that section, you'll find there are videos. We have a blog that I actually wrote several blog entries, one of them being what are the shelf life of cones. And there's some things in there about atmospheric effects, what kind of things happen to cones, how can you use a cone to troubleshoot a firing. So that's kind of unique what happens with cones, in that they very closely simulate the actual bodies that you're firing in your kilns, in that they're very sensitive to changes in atmosphere, whereas you might not see the behavior in your clay body, but they will manifest that problem faster or quicker in a cone. Mainly let's say your air to gas ratio is a little bit off in one firing, where you're trying to get an oxidizing firing, but the ratio gets mixed up somehow, and now you're slightly reducing. And you wouldn't really know that from looking at your glazes or your fired body, But if you were to see a cone in there, that cone would have some kind of telltale indication. It would either look a little off discolored, it could be bloated in some way, or you're going to see something that's not normal when the cone is observed seeing something like that in a firing. So they can tell you something beyond just temperature by just some history or use in time. You're going to be able to see, okay, I know this, when I have a good firing, my cone comes out shiny and glossy, but when it doesn't, why is that? And we have some of those reasons listed in our website, and it can help you to determine whether maybe I need to refire this, or maybe there's going to be some problem down the road that it's not quite to the temperature, so therefore I didn't get to the vitrification level, and there's going to be some crazing or some weakness in this clay body. Those are all things that you can actually do with the cones. The thing you can also find in that section are some of the charts that we have compiled. It's just a shortened list. It's not you can find the full list of cone 022 to 42, but a lot of you may not need that. So we have shortened a list up from cone 022 to 14. And that's probably the most commonly used groups of cones that you would ever encounter. At this point, I would be happy to entertain any questions that I didn't address as I was talking. So I'm going to open it up at this point to anything anyone would like to share.
You're muted, Paz.
Sorry about that. So we have one question that's popped up, and that's, are cones still accurate if they've gotten wet or frozen? And thank you so much for the fabulous information.
Yeah, that is I should have addressed that. Yeah, if cones were to get wet, you're going to actually break down the binder that's in the cone somewhat, so that it makes them very fragile and brittle once they're dried up again. You won't really know that until you go to fire them. So I would like to say, if you suspect that your cones have been exposed to moisture, a real easy way to check that is to just take them as if they're a piece of rope between your fingers and just give them a slight tug. If there's any weakness because the binder is broken down, that cone is just going to split apart through just the action of a tug of war that you're putting it under. Once that binder breaks down, they can almost revert back into those individual grains of beads that we formed before we pressed it. So there is some squeezing action that goes on, but that binder is really crucial to keeping that cone intact before it gets fired.
I have a question.
For it.
This is Victoria. I still don't know if you can hear me or not.
Yes, we can hear you.
Oh, great. I got fascinated a long time with the term eutetic, E-U-T-E-T-I-C, which I'm sure is very important when you're forming cones. But let's say I want cone 09. No, that's not a good one. Cone 9. That's an oddball. How on earth do they form it? Using the silica to alumina ratio, and then you have to have all these other materials to make it melt at the right temperature.
Well, cone 9 is particularly a porcelain body. And so if to form porcelain, you need silica, feldspar, and an alumina of some kind, and you could form that from a number of materials. But when we're sticking with a defined formula, and it's very common. You can almost look up, I think some people here were talking earlier about Insight, the Tony Hansen website.
Mhm.
If you went to a porcelain body formulation, it would almost mimic that of the Orton pyrometric cone.
Tom, first of all, pause. I want to thank you for finding this wonderful gentleman. But I think what I'm trying to find out is this term eutectic. When you're doing O22 up to what, cone 32, I think you mentioned, how on earth do you formulate all that?
Well, the science behind that is it's not the eutectic is a different thing altogether than what we're talking about with the silicon alumina ratio.
Ah,
A eutectic is something that you would look and find if you were to find something called a phase diagram for materials. So there's eutectics form between certain material compounds, and the eutectic is actually a melting phenomena, so that if you hit a specific ratio of, say, sodium and chlorine, and this is a binary phase diagram between two materials, one being chloride and the other being sodium. When they combine to form sodium chloride, you now have a salt that, when it gets to a certain temperature, will melt at a much lower temperature than the individual components of chlorine and sodium do by themselves. You can actually expand this out further. We've got hundreds of phase diagrams that have been developed for ceramic materials. So they can take silica on one spectrum and alumina on the other. And when you combine the ratios from 100% one to 0 on the other, and then the whole spectrum of ratios, they found that they will melt at different ratios as you go along. But there is one point where you hit a specific range of, say, 55% of one and 45 of the other, that you get this dive in temperature. And that's what they call a eutectic. We don't use that for formulating the cone.
I'm blown away. Thank you very much.
Mm.
I have a totally different interpretation of that word.
Okay, we've got another question. What's the shelf life of a cone?
Amazingly, there is no shelf life. I've got cones that were formed, I actually have cones from the 1910 era that are still at Orton that I could fire them today and they will perform the same as they did the day they were made. The key is keep them dry and don't get them wet. And therefore they will work. These are materials that we've dug up. They've been extracted from the earth and they've been sitting there as clay compounds or feldspars. These are just minerals. And so, and the binder that we're using, they're organic binders. So if there's nothing that's, moisture is going to attack those. So as long as you don't do anything to affect the integrity of those, the binder and the ratio of things that we've mixed together, it's going to last forever.
I have a question. So looking at like cone charts and like in general, there's a temperature for 108 degrees an hour and 270 degrees an hour. That's the basic spots that have been chosen on whatever the melt line is. Are there other rates that are available? Like do you have melt charts that are more
Yes.
complete than that?
Yes, there are. We don't like to publish the whole list for everyone to see, but if you have a specific cone that you're wanting to look at, say it's cone 9, we have over 100 years worth of data information compiled that we can tell you whatever heating rate that you're using, what temperature that cone is going to bend at.
Mm-hmm.
I didn't, you can find my email address on our website. And if you're interested in finding that specific chart, I can
Right.
email it to you.
Yeah. Okay, great.
Yeah,
Because I mean, for me, it's like 9, 10, and 11.
sure.
And like, depending on the atmosphere in the kiln, depending on the amount of mass of what's loaded in the kiln and the weather, at the end of some firings, I'm going 70 degrees an hour. Other firings is 20 degrees an hour as
And you want to
as
know,
the kiln's ending. And I mean, I know that it's giving me feedback as to how my clay and glazes are melting. There's a relationship there, but I don't have any temperature reference.
right?
Yeah.
So what this chart is it's a very specific chart, and a cone will deform when it starts to get within a certain firing window. So
Yeah.
you can take a cone 9 and you can take it up to cone 7 temperature,
Mm-hmm.
and you could hold that temperature for 3, 4, 5 hours. Cone 9 is not going to come down because you're at cone 7's temperature. You have to get within that firing window for cone 9, and it could be reached in any infinite number of combinations of ways.
Mm-hmm.
But until you get to that, you'll see on this chart, there is a defined lowest temperature and lowest rate that you're going to be able to get to, or the maximum firing temperature, in fact, and rate, and you're going to get within that window. And it's not a square window, it's kind of stretched to be able to see how that actually works.
Yeah.
And those charts can probably help you do that. So when you look back at those charts we do produce and put on our website, you see those numbers. You see 27, 60, and 150, say in degrees centigrade, or 15, was it 108, 270 on the top columns.
Mm-hmm.
I don't like to talk numbers with people when we're talking about those charts. I like to say, just throw away those numbers and replace them with the words slow, medium, and fast. So if you want to know how to get to cone 9 on a medium firing rate, go to that 106 column and just write the word medium, and that's going to tell you on an average firing,
Mm-hmm.
that's the temperature you're going to achieve. And the temperatures we
that
put
makes
on
sense.
there,
I get it. That all makes sense. I like to see a more granulated curve. I'll email you.
absolutely.
Thanks.
Yeah.
Yeah, thanks.
Bill?
Yeah, I have a question. I'm curious if there's any set range from the time a cone, like a cone 9 or a cone 10, when the tip starts to go to what actually touches down. How many degrees are we talking about in that process for a single cone?
Yeah, that on average, that is about a 17 degrees centigrade range from the time a cone starts to bend to when it comes down. But that is dependent upon the cone composition. And I'm glad you asked this question, because if you go back to where I was talking about the evolution of the self-supporting line, the original series of cones, we call them our B series. The reason we came up with the self-supporting is there was a problem that they encountered with the original series. Cone 4, 5, 6, 7, and 8 in the original series, when they start to come down, they come down over like a 9-degree range. It's fast, and they come down fast. And it was just not slow enough for those who were using them to actually get accurate information. So the engineers at Orton in the 70s developed the A series, the alternate series, to use for the self-supporting cones. And they actually doubled that bending range from that series of cones. So it's more gradual. And it is important to note that when a cone starts to bend, it starts out slow. And then as gravity starts taking effect, as it passes the 3 o'clock position, it may take 10 minutes to get from upright to the 3 o'clock, and then it'll only take maybe 6 minutes to go from 3 to 6. So it speeds up, it comes slow, and then bam, it's down. So we needed to expand that, and that's why we came up with that self-supporting cone series.
Great, thank you.
So we've got one member who said, thank you for letting us know that the Orton Cone Box show is still happening. They've always wanted to enter. So we'll make sure people have that web address in one of our communications to members so that if you want to explore it, it will be there for you. Got another question. I was always told that if I had to stop a firing, i.e. turn the electric off, that I would need to replace the cone in the sitter before refiring. Is that true or rumor?
I think it's good practice to do that. If it's an early on stage of the firing, and you haven't got really above 500 degrees, you could probably use that cone over without replacing it, but why risk it?
So then we want to know, are cones better than bars for kiln sitters?
No difference. There absolutely no difference between a small cone or a bar cone. They're made from the exact same material. The only difference is the shape. So pyrometrically, they're going to bend at the same temperatures. The difference I get from our customers is preference. Some feel that they can take that small cone that's wedge shaped and position it right or left in the kiln sitter to affect the firing of the kiln, to maybe shut it off a little sooner or a little later. Whereas the bar cone, it's straight across, there's no adjustment. I've done studies on this, and I have to tell you, you're only affecting it by maybe 1 or 2 degrees centigrade. And the accuracy of that kiln and what you're firing isn't being affected.
So then we have a question. Did you say that the colorant in cones is food coloring?
Yes. Yep. That they start out, say, orange, yellow, pink, lavender. That's just food coloring. That'll come out at about 300 degrees centigrade, burns away. And then if we didn't put food coloring in them, you'd see almost white cones across the board. Maybe a slight shade of gray, but they'd be hardly distinguishable.
When did you start doing that?
That was done in the 70s when they started making the self-supporting line. So they had a customer in a sanitary ware plant. The sanitary ware kiln foreman was having to line the cones up ahead of time. He liked to make all of his cone pats, and they wanted an easier way to distinguish between the cones. So they started to put color in them, and they loved it. So it's kind of a pain because you're at the discretion of the food dye companies, and we haven't been always able to get the exact same shade every time. So when you see a shift in one cone to the next and it's not exactly the same shade, that's because we couldn't get the same dye of food coloring.
I'm always grateful because reading those little numbers that are stamped on there sometimes is really hard.
I'm making a change to that, and it's slowly being implemented. Hopefully you guys will start seeing this, that the numbers that we're imprinting on those cones have gotten much larger and more legible. So that's my institute to the cone manufacturing over 20 years.
Thanks.
Hope they continue it, but yes, I wanted to do that.
Okay, another question. Is the 3 o'clock position considered done?
No. Your cone is about half done when it's at 3 o'clock. Done is at 6 o'clock. And the 6 o'clock position is in a self-supporting cone. You'll see that there's a line at the base of that cone, just at the bottom of the triangle. You'll see where there's like a demarcation line. It's about a half inch up from the base. So if the cone were to come down level to that line, that would be the end point of a firing. That's 6 o'clock. A lot of times the cone will continue down and the tip will touch the shelf. And that extra half inch is about a 1 to 2 degree change in temperature. But if you're shooting for when the cone is done, you want it to be a half inch above the shelf. And that's the same for the large cone as it is for the self-supporting.
That's good information. I never saw that
Yeah.
line.
Now,
We have one member who has a visual question, and it's Jeannie.
Yes, I just for the first time used self-supporting cones, electric fire cone 5 and cone 6. Now, is my kiln firing like it was a 10-minute hold? Should this have been melted, the cone 5 more? And I'm surprised that the cone 6 was kind of starting to bend. Is that typical?
that is typical. And that is affected by each cone composition is not equidistant spacing between when they
Okay.
start to bend. So sometimes they're close together, sometimes they're far apart. The reason why you see we made a cone 5.5 is because the difference between 6 and 5 is greater than most firings. So we put a 5.5 in between it. That 5 that you've got right there, if you said you put a 10-minute hold on it,
Yes.
if you added another 5 to 6 more minutes, that would be down to the 6 o'clock position.
And
The
then that's where
sixth,
it should be then.
yeah, and or you could increase your temperature to get that to come down by about 4 or 5 degrees, and you'll get you either get it through increased temperature or extended time.
Okay. All right. It was my first time testing the kiln to see if it was, firing to what it was supposed to say it was doing.
Yep. I'm glad you had examples. That's perfect.
Yeah, they just came out of the kiln yesterday for the first time. So thank you. I will add another 5 minutes and test that out.
Okay.
Thanks.
You're welcome.
This is a question probably many of us have. What is the best way to separate the self-supporting cones?
Oh, I wish I had some sitting here for you. The big base that you see, the triangular base on them, when they're joined together, if you have, you hold it with your finger and thumb and pinch it, and you just give it a slight twist. So that should be adequate to get them to break along that thin parting line.
All right, Myra's got a question, I think.
Yes, I do. I've been using the cone plaques for a long time, and I know that there was a change in how you position the cones in them. When I started, you put them in from the top, and you had them all lean a certain way. And then the latest cones, and it's not that recent, they ask you to put them in from underneath. Is that accurate? Or is it the same?
You have
Is the
found,
top part is shorter?
we manufacture a plaque that is where you put it in, but there are other companies that are manufacturing cone plaques that are not from Orton. And they're what we call those the blind hole plaque. They work fine,
Yeah.
but you just push them in through the bottom to get them into
Right.
that plaque. They have sort of like little 3 ridges on them.
Yeah.
Yep. Yeah, I've seen those before. Those are not made by Orton.
Well, I've been using them the way I used to use the regular cone plaques, but I didn't know if there was a difference in how they read temperature.
As long as
If
you
they
can
were
see
put-
that they're held at the 8 degree from vertical position,
Mhm.
that, and you're
So-
consistent in what you do, you're going to get good results.
Because even with that short tip showing, it's different than the whole cone showing.
Yes.
Okay, thank you.
Another question, are self-supporting cones better than large cones?
Depends on what you mean by better. If you like the fact that you don't have to worry about the mounting angle and the height of the cone, and you want to be able to just be free of having to put all of that together in a plaque, there's no question the self-supporting cone is going to get you there quicker. The accuracy of a self-supporting cone is double that of a large cone, because we have taken away the variability that could be associated with it. But if you take good care and practice, you can equate the large cone to the self-supporting. They're made from the same materials. They're characterized the same way. They should perform the same as long as you're diligent in what you're doing. People seem to like the large cone for the fact that you get 50 in a box versus 20, 25, and they're less expensive because you don't have that extra material that and engineering that we've put into it. Preference.
Right. Other questions out there? Okay, we'll do a last call. All right.
I thank you for letting me talk to you all. That's really great to see that. I have to tell you that over this last 3 years or so, with the pandemic and everything that's happened, there has been a resurgence in ceramics.
Yeah.
We see it at Orton, and we're having a very difficult time making the cones to keep up with it. So thank you. And I hope you all continue.
Thank you.
very much.
Thank you
Thank
for
you.
taking the time tonight and staying up late to hang with us.
You're welcome.
So we'll get, Tom's address is really very obvious once you get to the Orton Ceramics homepage, and we'll get the information on the Orton cone box competition out to people. So thank you all.
Thank
Thank
you.
you.
Thanks, Tom.
You're all
Thanks
welcome.
very much.
So we're gonna turn it back to Win.
Okay, there were a few people from the board that had announcements to make. So one is, let's see, oh, Jen, she had to leave. I think, did she come back? I don't see her name here. Okay, so I don't know what she was gonna say, something about the next jury, but I don't know what she was gonna say. I don't have that info. Stacy?
I just want to say that I'm going to put the link to the website up on the chat where you can sign up to do your team service at the Ojai sale, which would be a good place to do it because it's really a fun event. So I'm just going to put that up now. I just hit the wrong button and turned my camera off.
Okay, Brenda.
Barbara, could you share the screen? I have a slide.
Brenda, you should have access to share the screen.
Okay, thank you. Okay, I want to see this one. I thought you might be curious about how our membership is going. This is the information that I prepare for the board of directors every month for the board meeting. We've got 152 members as of yesterday, because I'm getting this ready for Stacy. So we've got 53 regular members, which is about 34% of our members. So we've got singles, couples, patrons, and 1 student. The plus, we have 99, which is about slightly over 65% of our membership. So we've got like this many singles, this many couples, this many patron plus. We have several categories of non-paying members. The lifetime, when you recognize somebody as a lifetime member, and the directions for doing that are in the bylaws, they get a free membership. We've got 3 residencies that are still, I hated to say the word, serving their membership time, and 1 student award left over from last year. So we 6.5% of our members are patrons, and we've gotten a lot of new members. We've got 14 out of the 152 are new members this year. And I'll continue to get membership until September sometimes, or even October. So what else have I been up to? Well, I emailed the directory out to you, and I received some good revisions, and then I revised it, and Terry's going to post it on the website. I think the version's 22.02. We did a survey on the membership form that you filled out when you joined this year. We asked, what type of telephone do you have? We've got 18 landlines and 130 mobiles, 34, which isn't surprising. We asked our guild members, how do they, how do they get information from us? And there are 4 sources: the membership IO, the website, the newsletter, and meetings. And there were 12 members that picked all 4 of them. They're not particular about where they go. But we had 109 members that chose got their emails along with some other sources. But interesting enough, 34 of our members, which I don't know what percentage that is, 34 of our members, this is the only way they get news from us, is through those emails. I was surprised at that. There are 41 members that listed the website as their source. Congratulations, Terry. 89 members listed the newsletter as a source. So Rudy's doing a great job. And we had 4 that this is their only source, and then 33 from the members. So I thought you'd be interested in that. If you have any questions, you know where I live.
And then Ellen Wolstatter couldn't make it tonight, so she asked me to make this announcement. If anyone who's juried who wants to participate in the gallery's Mother Day vase promo, to contact Ellen Wolstatter by email or telephone. She's in the membership directory. She's on the website, info on the website. And I think you just have to be a jury member. That's what I had. Is there anyone else that has any announcements? Lynn?
We talked about it briefly, but the letter with the websites for ordering clay and supplies will be coming out shortly, very shortly.
Thank you. Is April 10th? Is that still?
That's still the final
working? The deadline.
That's the deadline. So I'm hoping to get the letter out tomorrow, and then start recording what you all order before the 10th.
Excellent. Anything else?
I hope that people are working on their Beatrice Wood showpieces. It's about time. We have that front gallery, so we have a lot of space there. And there's information in the newsletter and on the website. And I need all of that information to me by August 14th. So it's going to be here before you know it. So keep working on those pieces.
Oh, and before Beatrice Wood is the July meeting is the big reveal for the current clay challenge, which is organic and geometric.
And
Yay.
And the people that participate in that clay challenge can post their work for sale at the Ojai, at the online store for the month of August without really having to do any of the paperwork, but just try it out. And so that's an opportunity to try that.
Cool.
Anything else? I think that's it. Thanks,
have
Foz, for putting this
question.
together.
There's a hand up on Meredith.
Yeah, I have a question about the what she just said, that we could sell through the Ojai sale, but we still have to be juried, right?
Yes, everybody has to be juried.
No, it was sell through the online store.
Yeah, and it was
Oh.
online store.
Yeah,
If you're in the Beatrice Wood show, you can sell your piece through the online store.
yeah, but you don't have to be juried through the Pottery Guild to be in that, right? Okay,
Right.
thank you.
Oh, yeah, if you're talking about the Beatrice Wood Show, no, it's open to all members.
Yeah.
You don't have to be juried.
Okay, that sounds like we did it. Thanks, Foz, for
Very
putting it
nicely.
together.
All right.
Thanks for
That was
everyone
really interesting.
being here tonight. It was
That was good.
really
It
good.
was very good. Yeah.
Thank you, Foz.
Excellent.
Thank you,
Lynn
Boz.
and Nadia, do you want to stay and talk about your access to the clay order email?
Yeah, I just got the email. I saw it. If you want, we can. Yeah, that'd be nice just to go over that a little bit.
Okay, I'm signing off. Good night, everybody.